Good morning, everybody. Being 10:15, we'll get started with this session. My name is Ramon Padilla with Terracon. I'm here to moderate and introduce to you Dr. Jason Lloyd, and I'll read a brief bio of Dr. Lloyd. Dr. Jason Lloyd is the Bridge Steel Specialist, Western Market for the National Steel Bridge Alliance, a division of the American Institute of Steel Construction. He represents the steel bridge industry on matters of steel bridge fabrication and construction. Jason's role with NSBA is to provide technical assistance, tools, and resources for steel bridges to bridge owners, designers, fabricators, university programs, and technical committees. Prior to joining the NSBA, Jason spent 7 years as a research engineer at Purdue University's Bowen Lab and Esbright Center, where he specialized in full-scale fatigue and fracture research, field testing of steel structures, and repair and retrofit of steel bridges. He earned his MS and PhD from Purdue University. He is currently a licensed professional engineer in the state of Indiana and a former U.S. Navy Seabee. One quick note in regards to questions, we'll compile questions and leave them for the end of the presentation. And with no further ado, I'll pass it over to Dr. Lloyd.
Yeah, thank you, Ramon. I appreciate that introduction. Hello, everyone. Thanks for joining me today as we revisit the topic of redundancy in steel bridges. At a glance, this slide kind of looks like the back bumper of a Volkswagen van or something, perhaps. But before moving on, I need to give credit to the many incredible researchers and engineers who have performed the work we are discussing today. My presentation represents all of our collective efforts. The research we'll be discussing was performed at Purdue University under Professor Robert Connor, but this slide indicates where each person who participated in the different parts of that research are now currently working. This is the outline for my presentation. I'm going to take just a brief moment at the beginning to talk about a little bit of industry perspective, borrowing from a chapter in another industry, in fact. I'm going to provide some historical perspective in terms of steel bridges in our industry and where we have come from and how we ended up where we are. Then I want to get into the research for system redundant members, internally redundant members, referred to as SRMs and IRMs respectively. And then we'll wrap it up toward the end and take any questions that you might have. First, the definition of risk to ensure we're all on the same page. Risk is the product of likelihood and consequence. A high or significant consequence with a very low likelihood renders a low risk scenario. On the contrary, high likelihood along with significant impact renders a high risk scenario. We'll be discussing the balance of these variables of risk throughout this discussion, but I need us to keep in mind that in these new Ashto guide specifications that I'm going to explain later, we are conservatively ignoring how likely something is to happen, and instead we assume in the analyses that it's already happened, no matter how unlikely it actually is, and then we analyze for the consequences. I'll give you a moment to read this cartoon. I wanted to touch on perspective because perspective does matter. Our perspective makes a difference in how we view circumstances and situations. So I wanted to begin today's presentation by dipping briefly into aviation history to borrow some perspective and hopefully set us up to revisit redundancy of steel bridges in a new light. According to the Smithsonian Institute, the Wright brothers made the first sustained, controlled, and powered manned flight. They did this in North Carolina in December of 1903. Since that time, aviation innovation continued attempting to improve powered flight in terms of weight and lift, thrust and drag, right, in order to improve speed, maneuverability, and altitude. One of these innovations was the triplane, like the Sopwith triplane shown in the top image, which is dated 1916. These planes had shorter, lighter wings for more lift, wider field of view, and improved elevator response. However, monoplanes like the Bristol M1C that you see in the lower image are reported to have having been flown around the same time period, maybe even earlier. These planes had some advantages over multi-wing planes, which I'll mention in just a moment. But the Bristol plane wasn't employed much during World War I like the Sopwith was, due to a perceived redundancy drawback. So the British High Command felt it was unwise to risk their pilots' lives with an aircraft with only a single wing. So if we set aside the redundancy of the wings for just a second, powered monoplanes had the advantage over the multi-wing planes of reduced drag by eliminating the exposed bracing between wings and internally carrying all of those wing forces. The monoplane had superior aerodynamic efficiency, allowing faster flight, but also required higher powered engines to fly the heavier frames. The multi-wing plane had superior structural efficiency of the frame, allowing smaller and lighter wings, lower powered engines, and slower stall speeds. Such as was the case for aviation, the challenge of engineering is often balancing the trade-offs between different performance characteristics. And of course, cost, right? We're always balancing cost. As aeronautical innovation continued with significant advances in the understanding of aerodynamics, engines became more powerful while wing materials became lighter and stronger, moving the aviation industry almost exclusively toward the monoplane designs that we mostly see today. Powered flight took off. So maybe now you're wondering how this relates to steel bridges, or if maybe I'm presenting at the wrong conference. But my good friend and mentor, Professor Robert Connor, started, started facetiously, wow, my throat's giving out all of a sudden. Started facetiously making a comparison between a fracture critical member in a bridge and the wing of a monoplane. On occasion, while presenting on the redundancy topics, we'd come across an engineer who was uncomfortable with non-load path redundant members and steel bridges, but who didn't seem to have a problem with flying to the conference on a monoplane. It kind of begged a somewhat humorous question for us. Why wouldn't that engineer also insist on flying on a multi-wing plane or a plane with multiple sets of nose gear in order to have load path redundancy during their commute at 36,000 feet? I wonder if it was a matter of perspective. Clearly, the aviation industry is motivated to use reliable and redundant structures. So why don't they use multi-wing planes for the case of catastrophic wing failure? But they also saw advantages in the monoplane airframe that were worth pursuing. Well, the simple answer is that instead of giving up on monoplanes, they developed alternative methods to design, fabricate, inspect, and maintain critical elements of their airframes, exploiting forms of redundancy other than load path redundancy, such as fail-safe and damage-tolerant design methods. These methods recognize that structures must withstand service loads, even when damaged or cracked, until reliable inspection methods can identify that damage. Clearly, with a little perspective on how the aviation industry has innovated for efficiency in their designs, we can take perhaps a chapter from their book. While managing performance risk, let's take a look at some historical context for steel bridges. Where did we all come from? Well, that's sadly a question I can't answer. It's a philosophical question that goes way beyond the scope of this presentation. But I can provide some historical context for how we got to where we are within respect to redundancy and fracture critical members. So let's step back in time just a little bit. Following the infamous collapse of the Silver Bridge over the Ohio River in 1967, the Federal Aid Highway Act of 1968 originated a requirement for the Secretary of Transportation to establish the National Bridge Inspection Standards, or the NBIS, to help ensure the safety of the nation's bridges. The NBIS is overseen by the Federal Highway Administration and is defined by the Code of Federal Regulations. Later, the Federal Highway Act of 1970 limited the NBIS to bridges on the Federal Aid Highway System. However, the Surface Transportation Assistance Act of 1978 extended the NBIS requirement to all bridges greater than 20 feet on public roads. In 1974, Ashto added the first fatigue design provisions and CVN minimums for material toughness based on extensive experimental research by John Fisher out of Lehigh University. In 1978, Ashto published the first edition of the guide specifications for fracture critical non-redundant steel bridge members, becoming known as the Fracture Control Plan, or FCP. This was the document that introduced the term fracture critical member, in fact. It implemented reduced fatigue stress range limits and improved fabrication quality control measures for FCMs. It was a few years later that the partial collapse of the Minas River Bridge happened. This was caused by pack rust that pushed one of two hanging bars off the pin at a pin and hanger detail. The other bar then fatigued and eventually fractured, leaving no connection for the supported girder. This likely motivated the Surface Transportation and Uniform Relocation Assistance Act, that's kind of a mouthful, of 1987, which expanded the scope of bridge inspection programs to identify fracture critical members and establish inspection procedures for them. So this left a gaping question. How did we know what to inspect at arm's length? Or in other words, what was a fracture critical member? So we began to rely on load path redundancy. It was the expedient answer, you might say. And as an industry, we became very comfortable with many girder lines and uncertain of anything less. That uncertainty was perhaps reinforced for some by the relatively recent and tragic collapse of the I-35 bridge in 2007. However, the collapse was actually caused by a design error that resulted in a buckling-induced failure mode. It was not a result of fracture, nor was it related to FCMs. Yet prominent documents such as the Bridge Inspector's Reference Manual and countless fracture-related papers and presentations continue to incorrectly promulgate it as a collapse related to FCMs. While all three collapses are tragic, only the Silver Bridge was a collapse caused by the fracture of the fracture critical member. It was the result of brittle high-strength steel utilized in a fatigue-prone detail that could not be inspected during a time when bridge inspections did not occur. These clearly are practices and materials that we no longer use in the design and fabrication of modern steel bridges. So maybe you're wondering if there have been other fracture critical members that have fractured. Well, the answer to that is yes. There have been several FCMs that have fractured, all of which were fabricated prior to the fracture control plan. And I've listed them here for you. And there are also some photos you can see. So naturally, your next question might be, how many of them resulted in partial or full collapse? Well, none of them actually. So maybe now you're wondering, well, how many fracture critical members have fractured that were fabricated to the fracture control plan implemented in 1978? Well, if we make no exceptions and we count all of them, it's 0. That's over 40 years of practice with 0 incidents of occurrence. That makes likelihood very, very low. We have to keep in mind that just because we used to do things a certain way doesn't mean we'll always do it that way. The steel bridges of the past are not the steel bridges of today that have infinite fatigue life, improved detailing, high toughness steel, proven welding processes, strict controls on repairs, and reliable shop inspection protocols. So knowing these things and with the anecdotal evidence in mind, it left industry leaders asking really good questions like, in the absence of load path redundancy, how can we identify what is actually a fracture critical member? What load case would be appropriate and what level of analysis should be required when determining that redundancy? And if a member is found to be redundant, can we link the damage tolerance and the inspection interval? In seeking answers to these questions, we were led to these 2 new Ashto guide specifications. So let's go ahead and take a closer look at these. The top one is the Ashto guide specifications for internal redundancy of mechanically fastened built-up steel members. Member level or internal redundancy prevents the partial or full collapse of a bridge following failure of a single component within an internally redundant member, or IRM, by redistribution of load into adjacent mechanically fastened components of the member itself. The bottom specification is the Ashto guide specifications for analysis and identification of fracture critical members and system redundant members. System level redundancy prevents the partial or full collapse of a bridge following failure of a system redundant member, or an SRM, by redistribution of load through the interconnected system of primary and secondary members as well as the deck. So let's dig a little deeper into the development of the guide spec for SRMs first. The essence of this guide specification is a standardized federal highway approved method for the analysis of systems for system level redundancy. It codifies the level of refinement of the analysis, the demands or the load combinations for a target reliability, and establishes acceptable performance criteria for a bridge in the faulted condition. There were 4 major objectives of this research. The first one was the development of a finite element analysis methodology for redundancy evaluation of steel bridges. Once a benchmarked analysis methodology was developed, finite element models of existing bridges were then developed to calculate the dynamic amplification factors after the failure of a primary steel tension member. Thirdly, steel bridge fabrication and design procedures were reviewed to develop a set of recommendations to avoid occurrence of fracture. And then finally, a comprehensive set of specifications were written with the intent of providing bridge engineers with the methodology for the identification of FCMs and SRMs through redundancy evaluations and a set of requirements to prevent fracture in steel bridge members. The proposed specifications were submitted to Ashto's T14 Committee on Structural Steel Design for balloting and adoption. 5 primary structures were used to benchmark and calibrate the FEA methodology. These 5 structures were selected because, 1, they're typically considered to have FCMs, or at least to be considered to have low levels of redundancy, as well as having failure data available. Once models were built and validated by comparing to available data, they were utilized to study member out scenarios representing steel tension member failure in different locations. A 6th structure, the Dan Ryan transverse cross girder that fractured in the 1970s, was also used to develop the dynamic amplification factor. Once the necessary FEA procedures, techniques, and inputs for the redundancy evaluation of steel bridges were established, the FEA methodology was completed with the development of load case characterizing the loading conditions during and after the failure of a steel tension member, and then also the establishment of performance benchmarks that guarantee redundant capacity in the faulted state. The reliability principles utilized in the development of loading combinations described in the Ashto LRFD bridge design specifications, as well as the Ashto manual for bridge evaluation, were used to calculate the loading combinations applicable to nonlinear FEA for the sudden failure of a primary steel tension member, and for extended period of service between the member failure and its discovery. So performance benchmarks considering strength, stability, and serviceability of the faulted structure were compiled to set minimum performance requirements for typical steel bridges after the failure of a tension member. Next was the characterization of the loading conditions in a steel bridge after the failure of a tension member. A sudden failure, for example, brittle fracture, of a primary steel tension member is a high-rate dynamic event, and the post-fracture deflection is also a dynamic structural response event. The inertia of the deflecting bridge will amplify the static forces present in the post-fracture structure under static load conditions. Now, it's not usually practical to perform a dynamic system analysis to identify fracture critical members. So the researchers wanted to determine a simplified dynamic amplification factor that is multiplied by the static response of the bridge in the faulted condition, therefore accounting for these inertial effects. This amplification factor is applied to the load combination characterizing the dynamic failure event, which I'll get to in just a second. It's called redundancy 1. Data from the 2 university experimental programs were used to benchmark these dynamic analyses. Then the 5 previously mentioned bridges were also used to develop the factor, along with the Dan Ryan Expressway Bridge cross girder that fractured in 1978, as well as 11 more continuous twin tub girder bridges of varying geometry. A load model was developed using reliability theory. The approach used to develop the load factors is consistent with that used in the development of the existing Ashto LRFD bridge design specification. The reliability analysis utilized the statistical parameters described in SHRP2 report entitled Bridges for 100-Year Service Beyond 100 Years, Service Limit State Design, as well as NCHRP report 368 entitled Calibration of LRFD Bridge Design Code, which was also used in the development of the Ashto LRFD load factors. As you can see on this slide, there are reduced load factors for bridges fabricated to the Ashto AWS fracture control plan versus those not so, which, as you can imagine, is due to the reduced likelihood of fracture occurring in those cases. There are two primary load combinations, redundancy 1 and redundancy 2. Redundancy 1 evaluates the ability of the bridge to immediately survive a sudden brittle fracture. The load factors developed for redundancy 1 correspond to a target reliability factor of 3.5 in the faulted state. Note, this load combination is not intended to produce the fracture, but to represent the average maximum load, in particular live load, that may be on the bridge at the time of a fracture. This level of reliability ensures with high confidences that the bridge will survive the initial fracture. Notice that this also includes the dynamic amplification factor, dA sub r. Redundancy 2 evaluates the ability of the bridge to carry live load during the interval between when the fracture occurs and when it is discovered. This interval is assumed to be between 5 and 50 years. The reason the interval is assumed to be between 5 and 50 years is simply due to the fact that statistical parameters for these two intervals are all that are reported in the literature. And interestingly, there's very little difference between 5-year and 50-year return periods. It's also noted that although 24 months may seem reasonable, it must be remembered that the objective of the analysis is to increase the inspection interval beyond 24 months for redundant structures. The target reliability factor is 2.5 for redundancy 2. These load combinations were accepted by the Ashto T5 Committee on Loads and Load Distribution. Refined finite element analysis may seem like a complex solution, and it is really, but it's also because it's a complex question. However, there are things our industry can do to simplify our approach. That will be the next step in the evolution of revisiting redundancy in steel bridges. They've already begun to do this actually in Wisconsin, for example, in which they've applied the guide specifications to many continuous twin tub bridges and have begun to develop simplified hand calculations that can be used instead for a bridge that meets certain criteria, including things like detailing, materials, fracture control, and certain geometry. Also, Texas Department of Transportation has recently added some simplified calculations to their bridge design manual for new twin tub girder bridges and system redundancy. So looking further down the road, we hope to see families of bridges that, if meeting established criteria, a particular bridge could be adopted into a family of bridges whose primary members are automatically designated as system redundant based on known performance of that family's characteristics. All right, so let's take a look at the research that contributed to the IRM guide specifications next. The essence of this guide specification is to provide a quantitative approach for the evaluation of mechanically fastened built-up steel members. It adopts the redundancy 2 load combination explained previously, giving the user guidance for evaluation of existing members, as well as new designs. But before I continue, I need to mention that there currently is a hold on the implementation of this guide spec. So background on that is in 2012, Federal Highway released a redundancy memo in which Federal Highway formally recognized system redundancy. But at the time, the IRM research was still ongoing, so they did not accept internal redundancy as a way for owners to avoid fracture in fracture critical members for non-load path redundant members. A revision to that in 2012, a revision to that 2012 memo has since been drafted to fully accept this new Ashto guide specification. And I know this personally because I was one of several people that provided feedback to Federal Highway in the drafting of that memo. The holdup, however, is that the current administration won't allow any new policies, which means the memo cannot be released. So it's sitting on a Federal Highway desk, so to speak, somewhere, and we're anxiously awaiting its release so that owners can begin to implement this new Ashto guide specification. All right, so with that then, let's take a look at the research behind it. The primary objectives for the research included experimental testing to determine if a running fracture could propagate across component boundaries, experimental fatigue testing of specimens in the faulted condition, meaning having a single component fractured, to determine the after-fracture fatigue life of the remaining cross-section, calibration of finite element models to support a parametric study needed to develop amplification factors that account for local stress concentrations due to load redistribution, as well as to quantify any secondary effects. And then finally, proposed specifications that were submitted to the Ashto T14 Committee on Structural Steel Design for balloting and adoption. We performed large-scale fracture tests of built-up bolted and riveted specimens. And there was a mix of axial, which you can see on the left side of the slide, as well as flexural, which you see two side-by-side specimens on the right side of the slide. The fracture process was quite challenging to accomplish. First, we had to initiate and grow a fatigue crack in one component of the built-up member. And we do this by notching the desired component and then putting it through constant amplitude cyclic loading until a critical crack length had grown. Next, we'd cool the specimen to a temperature at which it had single foot-pound CVN values, meaning the steel was at a lower shelf toughness for the fracture event. And for any of you that aren't familiar with CVN tests or toughness, this means we made the steel as brittle as possible. The cooling process was performed using liquid nitrogen, and we cooled the entire cross-section, not just the fatigue cracked specimen, component, I mean to say. It may be difficult to see, but the axial specimen on the left is white due to the frost buildup that occurred after the cooling chamber was removed and then moisture in the ambient air cooled and froze against the surface of the steel. On the left now, you can see the cooling chamber wrapped around an axial specimen with nitrogen vapor escaping. The liquid nitrogen tank is in the lower left. Following cooling of the specimens to the lowest possible toughness, the specimens were then loaded to 0.55 Fy, or sometimes more, of the unfractured cross-section. Of the 20 specimens that were fractured, only one actually fractured at that stage. In all other cases, we had to implement a crack opening displacement at the notch using hydraulic wedges in order to initiate the brittle fracture propagation. I mean, it really was very challenging to do. These things were really difficult to get to break. We found that as a component fatigued, it would begin to unload to stiffer adjacent components, which relieved some of the stress intensity at the crack tip. Additionally, we theorized that crack tip opening was being resisted by adjacent components through fastener shear. So in some cases, we removed a row of fasteners to allow for localized displacement. The middle image shows the hydraulic wedges in place prior to fracture of a flexural member cover plate. And then the image on the right shows a large tack weld that was placed in the path of the running fracture on an axial specimen. We intended to see if tack welds on legacy riveted structures, because as you know, we often left those in place back in the day, which is not our current practice anymore. However unlikely it would be for them to be in the path of fracture, we wanted to see if it would provide a path for fracture into an adjacent component. The good news is that the tack weld did not, and as you can see now on the image on the right. The fracture tests were extremely harsh tests, and we found that fracture could not propagate across component boundaries and sever an entire cross-section. Cross-boundary fracture resistance is what we call this inherent resistance to running fracture of built-up members. Another very important takeaway from these tests was that toughness is not an essential material property for built-up members to resist fracture. This means that we can equally apply these approaches to legacy structures. A number of specimens were also subjected to fatigue testing following fracture of a component. The plot you see shows some of those results that were plotted with the Ashto fatigue design curve, having constant amplitude stress range along the vertical axis and the number of cycles along the horizontal axis on a log-log plot. Fatigue life in this case was the number of cycles from after fracture of the first component until a second component was significantly cracked. We tested both punched and drilled holes, high-strength bolts, and hot-driven rivets. The plot also accounts for amplified after fracture net section stresses. As you can see, punched holes resulted in category E prime resistance following fracture, and drilled holes came out as a category C. Again, keep in mind that this is fatigue resistance in the presence of a fractured component. The next step in the research was to calibrate finite element models to the experimental work. As I said before, the fracture tests were extremely demanding tests and covered a wide range of cross-sections and fracture scenarios. And they were intended to determine if running fracture could transfer across component boundaries. So knowing that it would not, the dynamic event itself was really not the goal of the finite element models. Instead, these were calibrated to static loading in the faulted conditions with the goal of capturing load redistribution behavior, including any secondary effects, so that we could develop local stress amplifiers that can be used in our favorite nominal stress equations like P over A and MC over I. This was an important part of the research because we needed to be able to predict the fatigue life in the faulted condition in order to calculate the inspection interval for an internally redundant member. So we did this through extensive parametric studies. So here are a couple of examples of the stress amplification factors. You can see the factors themselves highlighted in red font. The top is an example for flexural members and non-composite, where you have a beta sub AF, which is the amplification factor for after fracture of flexural members. And you can see how it's simply multiplied by one of our favorite equations of factored moment divided by after fracture net section modulus. So the lower one is an example for an axial member. There are two factors here. This is a new Greek letter, and I love it because it actually looks like a built-up member. So it's one of my favorite things, but this is the Greek letter Chi, and there's a Chi sub B for a local bending effect and a Chi VL, which is for shear lag. The final step in the research and in the evaluation, if you're evaluating for internal redundancy, for an internally redundant member is calculation of the special inspection interval. The special inspection replaces the arm's length FCM inspection without changing requirements for routine inspection. The IRM guide specs include a methodology to establish the interval for special inspections intended to locate any tension component that has possibly failed. This inspection of IRMs is referred to as a special inspection, just as it's defined in the Code of Federal Regulations, and must be of sufficient depth to reliably detect a severed component. Conceptually, this is a significant departure from the arbitrary calendar-based 2-year interval that's intended to find fatigue cracks. And based on what we know about probability of detection, internal redundancy may have been serving us well in our built-up members for a long time. To support efforts with IRM analysis at NSBA, we've been recently developing spreadsheet-based evaluation tools. So we currently have 2 spreadsheets and a user manual available for free download from our design resources webpage. One sheet will analyze a multi-component axial member and another will analyze a flexural member. It makes all of the required checks for strength and fatigue and then produces a special inspection interval according to the provisions of the IRM guide specification. There are a number of benefits that come with taking advantage of redundancy through SRMs and IRMs. First of all, the inspection objective is much different. They're not the same as they are for FCMs, or fracture critical members. We know that the member or other members in the system will carry load in the faulted condition. So we're no longer looking for those tiny fatigue cracks, but instead we're looking for a broken component. This means that the probability of detection, or POD, increases significantly and better aligns with the data we have for visual inspection probability of detection in steel bridges. In addition, we're now integrating the quality of materials, quality of fabrication, and damage tolerance with the inspection interval. So this really is the first step in truly integrating the fracture control plan using rational risk-based inspection intervals. In other words, the inspection depth and interval become tailored to the bridge or the member in question. It's no longer a one-size-fits-all. The way our current inspection program works, these 2 bridges are equals. We would be required to inspect these structures at the same interval and depth. Perhaps you might agree with me that we should be managing our inventory a little bit differently. So with these new Ashto guide specifications, we've taken the first step toward allocating inspection resources according to risk without compromising reliability. So let's bring this full circle now and consider the aviation analogy again. Monoplanes are not load path redundant, yet they have an acceptable performance risk because the aviation industry has managed to take advantage of member level redundancy, crack arrest detailing, fatigue prediction models, and inspection programs that are linked to the design, fabrication, fatigue life, and probability of detection. This means likelihood is low, and even though consequence is high, the result is low risk. So what about steel bridges? As we've talked about today, likelihood is very low, particularly for bridges fabricated to the fracture control plan. And if we have internal member redundancy or system redundancy, the consequence is also low, which gives us a low risk as well. Thank you for revisiting redundancy of steel bridges with me today. I'd be happy to take any questions for the remaining time.
Thanks, Dr. Lloyd. I there aren't any questions listed on the chat, but I did have a couple questions. Um, being on the geotech side myself, perhaps a little bit ignorant on the the software tools that you would use to evaluate a failure. What software tools do you typically use to model and evaluate failures?
Yeah, the guide specification for system redundant members goes into detail. It doesn't list specific products necessarily, but it will give some guidance on the capabilities that the software needs to have, including things like nonlinear material and nonlinear geometry. You get into shear stud behavior, concrete crushing, some of those more refined steps in the analysis. So as long as the software is capable of that level of analysis, then it should do fine. When it comes to internal redundancy, so the IRMs, we've taken all of the FE work and we've done that in the background in developing the guide specification. And so for most internally redundant members, there are a couple of exceptions that we couldn't get to, a big one being tie girders. So if you have a tie girder for maybe a new tight arch design and you want to implement built-up construction in that tie girder, we didn't have the ability, timing, and funding and that kind of thing to get to that specific type of member. So it's included in the guide spec. It can be evaluated, but you'll have to go through an analysis process in finite element to do that. But for all the other types, for pretty much any built-up axial member that you might see in a truss or flexural members, we've developed simplified solutions that can be implemented through a spreadsheet. And like I showed, we've actually developed some of those at NSBA that people can download and use for free. They can modify if they want to, and those types of things, or they can produce their own. The calculations are quite simplified for those cases.
Oh, thank you. A second question that I did have was, in the middle of the presentation, you had a few slides of the very fancy lab, recreating failures. Was there, a case that perhaps stuck in your mind where you modeled something and set out to test it, and it sort of, didn't quite show that and shed some light on something different?
That's a great question. I'm kind of going back through with all the testing in my mind, trying to think if there's one that stands out. I think in most cases, in the beginning, there was definitely a learning curve for us. Like I mentioned, getting those built up members to break was extremely challenging. We would use the linear elastic fracture mechanics equations to establish what would be a critical length crack. And a lot of those are based on a plate that's floating in space without really a lot of boundary conditions that do exist in built up construction. And so we realized that they wouldn't be super accurate, but at least it would give us a starting point, right? So we would calculate that critical length, and then we would take the member to that critical load. And like I said, it's cooled to a point where the steel is as brittle as possible. And then we would hope that it would fracture, because the test itself really needed to see a brittle fracture event, that sudden and violent release of energy. And what we found in the built-up construction, that it was very difficult, because as that crack was developed in one of those components, it becomes more compliant relative to the other ones that are connected to it through rivets or bolts. And as that becomes more compliant, it sheds load naturally to a stiffer adjacent component. And so that takes some of the demand away from that crack tip. And so that critical length is no longer as critical as we might be calculating. And so what we found in the beginning is that these built up members are much more efficient in terms of resisting fracture than we really give them credit for. And so what we had to do in the laboratory is force conditions that would never exist in real world. And that's where those hydraulic wedges come into play. So we would attempt to fracture, and if it didn't fracture on its own, then we would apply these hydraulic wedges into the notches. If you can imagine, what that does is that opens up that notch and forces a really intense crack tip opening, which drives up the stress intensity factor at that crack tip and forces a propagation of the fracture. And so of course that's not going to exist in real life. We don't have hydraulic wedges installed in notches, right? But that's what we found we had to do in order to force a brittle fracture event in these built-up members. It was really quite challenging. And so I think for me, that's the biggest takeaway, and something that going into the testing, we didn't fully anticipate, but we had to adapt to in order to make the testing work for us.
Well, thank you very much. Let me take a quick look. Okay, well, having no other questions, that concludes our presentation. Thanks again for the presentation. It was very interesting.
I appreciate that. Thanks. It was a pleasure being with you today.
Thank you. Bye.